Okay, so in the previous lecture, we were discussing about ring theory and we had introduced the definition of a ring and we had merely established a certain number of examples related to rings. In this lecture, we are also going to talk about certain important examples, but before that, we are going to introduce some properties, some specific properties which we should deal with. And then we will be again moving on to examples. Okay, so let me give this as a proposition. Let me just decrease the length of, yeah, okay, proposition. So let R be a ring, then number one is that 0 times a is same as a times 0 is same as 0. This happens for all elements in the ring. Number two is that minus a times b is same as a times minus b, and this is same as minus ab. Number three, minus a times minus b is same as ab. And number four is that if I consider the element 1 in R, then 1 is unique and minus a is same as minus 1 times. Okay, so let's go to a proof of this. Proof. Okay, now the first statement is pretty easily observable because see, I can write it like, so you have 0 times a, right? I can write 0 times a as 0 times a can be written as 0 plus 0 times a, right? But 0 plus 0 times a can be written as 0 times a plus 0 times a. Then if I consider the left cancellation or the right cancellation, I get 0 times a to be 0, right? This is a pretty trivial statement. What about the next statement? How can I prove the next statement? Okay, so number 2, let's see. Now observe that AB plus minus a times b, this I can write as a plus of minus a times b. Okay, now obviously a plus of minus a, that indeed is 0, so it's 0 times b because minus a obviously is the additive inverse of a, so this is 0. But then this implies minus a times b is same as minus ab. In a similar way, you can show that, I'm not doing that anymore, on a similar note, you can just consider the sum ab plus a times minus b, and then you can consider it to be a times b plus minus b, and do the same thing. You will get the same result, but then you have an equality, right? Okay. Number 3 is again sort of similar. How can we prove number 3? We can do it in this way, right? Observe that a so we have ab plus minus a times minus b. Now one thing which we already know is that I can write this straight away follows from 2. I can write this as ab minus a times b, right? But I can take this as a minus of minus a times b, right? Is it clear? But how can I follow out from here? So do we get anything interesting out from here? I guess we get 2ab, right? We get 2ab. So this implies that, so I can cancel out ab, so this implies minus a times minus b is equals to 2 is equals to ab, right? Okay, now number 4, The uniqueness part is pretty obvious, because suppose 1 and 1 prime are distinct multiplicative identities, then by definition we have 1 times 1 prime to be 1, because 1 prime is a multiplicative identity, and 1 times 1 prime to be 1 prime as well, because 1 is a multiplicative identity. So we have an equality of them both. This is pretty obvious, right? And the other part, I guess you should be able to do that. You can just use 2. So I will be just writing follows from 2. Just write out follows from 2. Okay, whatever. Okay, now let us introduce 2 more important definitions. Definitions. First thing, let me first write that let R be a ring. Let R be a ring. A non-zero element of non-zero element of R is said to be a zero divisor. Is said to be a zero divisor if there exists some element B in R such that AB is equals to 0 or BA is equals to 0. Clear? So this is the simplest example, or I should say the simplest non-conventional way of defining something which divides 0. I should say it like that, because intuitively in case of integers we have seen such concepts that we say that every integer divides 0. So in a way we have sort of generalized the fact. Hence the term of zero divisor, something which is dividing 0. I should also mention the fact that if there exists a non-zero element B, okay, B also needs to be non-zero, because otherwise there is no concept of saying a division, a divisor for 0 exists, right? Okay. Next thing, so this is one definition. I should write it like say number 1, and number 2 is that let R be a ring. A non-zero element of R is said to be a unit, if there exists some B in R such that AB is equals to 1, which is also is equals to BA. Clear? Okay. So in a way, a unit is an element which has a well defined multiplicative inverse in the ring. That's precisely what I want to say. So we define for all rings are the collection of units of R as R cross. I should write we denote as R cross. Clearly enough, R cross is a multiplicative group. Try and justify this out. It's a multiplicative group. Okay, it's a multiplicative group, and this multiplicative group is what we call the group of units again. Group of units. Clear? Now, can you follow some definition of a field with respect to this group of units? This is pretty immediate, that a ring, I shouldn't say a ring, a commutative ring with unity R is a field if the group of units of R is whole of the collection of R except 0, right? Because by definition of a field, a commutative ring with unity forms a field if every non-zero element has an inverse, right? Therefore, the group of units of R must be the whole of R except the zero element. And that is the condition for R to be a field, right? The next important observation, I should say, the next important observation I should speak about is that a zero divisor can never be a unit, right? And vice versa as well. So I am writing it like this, that a zero divisor, sec, a zero divisor can never be a unit. Why is it so? Because suppose you have a zero divisor, let's say A. So let me just explain this out. Let A be a zero divisor in any ring. In any ring, I'm so that's the reason why I'm not specifying a ring. So let A be a zero divisor, and let B be such that AB is equals to 0. Okay. Now obviously B is non-zero, right? Because from the definition of a zero divisor, A is a zero divisor where A is a non-zero element. If there exists a non-zero element B such that AB is equals to 0 or BA is equals to 0. So we are assuming that A is a zero divisor, hence A is by definition a non-zero element, and since A is a zero divisor, there exists another non-zero element which is B such that AB is equals to 0 or BA is equals to 0. Without loss of generality, we are assuming AB to be equals to 0. Okay. So such that AB is equals to 0. Now suppose A is a unit as well. Suppose A is a unit as well. So this implies there exists some element V such that VA is equals to 1, right? But then observe that now B is basically equals to 1 times B, but I can write 1 as VA. So it's VAB, but then I can use the associativity law to consider AB together. But then AB is 0, right? So this is 0. But that's a contradiction, right? Because B complemented the zero divisor, hence B is a non-zero element. So which is a contradiction? Which is a contradiction. Clear? Okay. A few examples, if I say examples. Okay, I should also, I guess I should include this here only, or whether I'll do it in the next lecture. Okay, let's do it here only. Definition: a commutative ring R, or let me say a commutative ring with unity R, is said to be an integral domain, is said to be an integral domain if R has no zero divisors. If R has no zero divisors. In some books, they also considered 0 itself to be a zero divisor as well. That is, they do not consider A to be a non-zero element for it to be a zero divisor. They consider it in such a way that one of them is non-zero in a way. Okay. So typically in that case, we say that a commutative ring with unity R is said to be an integral domain if it has no non-zero zero divisor. Okay. Clear? See, what they mean to say is that, what I'm trying to say is that, see, if so I have AB is equals to 0. Now if either A is 0 or B is 0, then this equation is trivial, right? If either A or B, that is if both A and B are non-zero, then this equation is sort of non-trivial statement. And in that case, we have actually the elegance of a zero divisor. Okay. If either A or B is 0, then that's not quite something very unnatural. That's what I'm trying to say. Okay. So in some books, they include 0 itself to be a zero divisor as well, because 0 multiplied with any element basically gives you 0. So in that case, we define an integral domain to be the collection of all, that is, it has no non-zero zero divisor. Clear? Okay. Now let us talk about a few examples. Okay. What can you say about Z? Examples. Number one, what can you say about Z? Now, clearly enough, Z cannot contain a zero divisor, and that pretty much follows from its arithmetic structure. Right? Z cannot have any non-zero zero divisor. We will go as per we defined. Z has no zero divisor, right? Z has no zero divisor. Z has no zero divisor. So this typically means that Z is an integral domain. Z is an integral domain. Also, what are the only units in Z? If you carefully follow, then only plus and minus 1 are its units. Because any element other than plus or minus 1 will have no unit, because at that point it will consider its reciprocal, but reciprocals are not closed under Z. Right? Okay. Number 2, let's say, if I talk about Q, then every element in Q except every non-zero element in Q is a unit. That's quite easily follows from the structure of Q. So it's basically Q minus 0. Obvious enough, it forms a field. For example, R will also form a field and C will also form a field. Does Q have any zero divisor? It cannot have, because every non-zero element in Q is a unit. So it cannot be a zero divisor anymore, right? Okay. Next, let us talk about Zn. Okay. Let us go by a very simple example. Let us talk about Z6. So Z6 contains the elements 0, 1, 2, 3, 4 and 5, and sorry, I mean to say so we are considering it to be a ring, right? So if I consider the elements 2 and 3, what is 2 times 3 modulo 6? Like, this is a ring with addition modulo 6 and multiplication modulo 6, right? So what is 2 times 3 modulo 6? So it's 0, right? But 2 and 3 are both non-zero. Therefore, 2 constitutes a zero divisor. So 2 is a zero divisor. 3 is also immediately a zero divisor. See, it directly follows from the definition that if A is a zero divisor of B, if A is a zero divisor where B complements A, then B is also a zero divisor where A complements B. In a way, what I'm trying to say is that I can define zero divisors as a pair. Okay, I can define zero divisors as a pair. That is, A and B are zero divisor, typically meaning that AB is equals to 0 or BA is equals to 0. Okay. So 2 and 3 are zero divisors in this case, specifically speaking. Surely enough, we can arbitrarily define zero divisors for any Zn till n is not prime. Zn always considers zero divisors for n not equal to a prime p, right? And you can think of it in this way, that if n was a prime, then n typically forms a field. So every non-zero element is a unit, hence cannot be zero divisors. But you can also arithmetically find out the fact that why it happens to be it happens to always consider zero divisor. That's precisely because of the fact that if I consider Zn, then I am actually admitting all the integers from 0 to n minus 1. Since n is not a prime number, so it must admit some factor of it, or one or two factors of it. If I multiply them together, I'll get n. That's the precise thing which I wanted to say. Right? Okay. Let us explore this a bit strongly. Claim Zn. Okay, let me write it in this way. A belongs to Zn is either a unit or a zero divisor. So let me precisely talk about non-zero elements. Okay, it is either a unit or a zero divisor. Okay, how can we do this? Now one thing which we know is that it is a unit if and only if n is prime, right? Every a in Zn is a unit if and only if, sorry, I mean to say that a in Zn, we are talking about units, right? So a in Zn is a unit if and only if a comma n is 1. That is the GCD of a and n is 1. This directly follows from how we established the concept of group of units, right? So suppose the GCD is not 1, suppose they are not coprime, suppose a n admits the GCD D which is greater than 1, okay. Then let B to be n by D, okay. Now D is greater than 1, since D is greater than 1, B must be less than n and it is obviously greater than 0 as well. But observe that n will then surely divide AB, which would imply that AB bar must be 0, or I can simply not use the complications of bar, I can simply say this implies AB is congruent to 0 modulo n, which means that A multiplied with B in terms of multiplication modulo n is 0, right, which means that A and B are 0 divisors. Clear? Okay. Now comes a very important example. Examples. This is called the quadratic field. Quadratic field. Okay. What we do is that we start with a rational number which is not a perfect square. Let D be a rational number such that D is not a perfect square. D is not a perfect square. What we do is we define a set. We define a set Q root D as the collection of all elements of the form A plus B root D such that A and B are rational numbers. Okay. We also define a conjugate for every element of this form. Let W be is equals to A plus B root D. Then we define W bar as A minus B root D. Okay. This is somewhat resembling the concept of complexes as well. Okay. Now how do we, now it's quite obvious that now we know that sum or some subtraction or addition of two rational numbers is a rational number. What we try to do is that we try to define operations on Q root D as component wise addition, right, and the multiplication we consider it to be sort of distributive. Okay. So we define A plus B root D plus C plus small d root capital D to be A plus C plus B plus D root D. Okay. Then surely enough this will come out to be an element of Q root D. Clear? Okay. Okay. How do we define a multiplication on it? So we define A plus B root D times C plus small d root capital D to be, so we just distribute it out. So A times C plus, see here we have B times D and with root D and root D there, right? So what I'm trying to do is that I am trying to separate out the root D part. That's all what I'm trying to do. Okay, that's exactly what I'm trying to do. So observe that, so B times D with root D squared, so it's capital D, plus here I have AD plus BC times root D. Okay, this is the way we are defining multiplication, and surely enough this is also an element of q root d, right, because this is still rational, this is still rational, here also this is still rational, and this is still rational, right. So we have defined a binary operation in some way. Furthermore, observe that what can I say about the identity in terms of this multiplication. What if I consider c plus d root d to be 1 plus 0 root d, then what should be a plus b root d times s? Then this should be surely, so a times 1 and the other part becomes 0, plus we have here b times root d and this part becomes 0, so I have a plus b root d. The other part will also come out to be same, so it surely has a identity, multiplicative identity. Additive identity is pretty obvious, right? Additive identity will be 0 plus 0 root d, right? Clear? So it is sort of obvious that these identities, both additive identity as well as the multiplicative identities, are just carrying forward from Q, right? There is no new element, no new identity coming out, right? Moreover, observe that if I consider any arbitrary element out from Q root D and I consider its product with its conjugate, let W be of the form A plus B root D from Q root D, then what is W times W bar? So it is basically A plus B root D times A minus B root D, but then surely this comes out as, if you carefully observe, this comes out as A square minus B square D, right? Now see, if A plus B root D is non-zero, then A minus B root D is also non-zero. Also, A square minus B square D is also non-zero. So if this happens, therefore I can write the inverse of A plus B root D as its conjugate A minus B root D divided by this value, A square minus B square, right? Hence, we are using the term a quadratic field because indeed this forms a field. Commutativity follows from the fact that Q is commutative, right? Because whatever manipulation we are doing here, it's all happening in terms of Q. So since Q is commutative, so is Q root D. Okay. Okay. Now comes a very important part, that do you guys know what are square free integers? So square free integers are the integers where we do not have the existence of any square element in its factorization. Okay. For example, what I mean to say is that if I consider its prime factorization, for example, then we do not have the square of any prime present except 1. The square of no prime is present except 1, or it is not divisible by the square of any integer greater than 1. I think that's a more clarified definition. An integer, let's talk about d only, or let's say d dash. An integer d dash is said to be square free if it is not divisible by any square of an integer. I should use by square of any integer other than 1. For example, 15 is 3 times 5, it's surely square free, while 16 isn't, because 16 is basically 4 times 4, but then this implies that 4 divides 16 and 4 is nothing but 2 squared, right? Okay. Now since D is the D we were dealing with, it was not a perfect square. D was not a perfect square. Therefore, uh, it it might be divisible by some square of some integer, by the square of some integer, but it's not possible that every prime factor it constitutes of in its prime factorization, it consists of even powers, right? Because if every prime factor of D would consider even powers for in its prime factorization, then we would surely be able to consider the square root of D, right? Or in other words, D would have been a perfect square back then. What we do is that we extract out the square part from D. Okay. So now we write, therefore we write D as f square times D dash, where D dash is uh, a square free part, is the square free part. Okay. That is what we are basically doing here is that suppose I consider the number, let's say 45. So 45 is surely not a perfect square. We can write it as 9 times 5, or this is basically 3 square times 5. So what I'm doing is basically I'm extracting out the square part. So I'm extracting out 3 outside and I'm only left with 5. So this is your D dash and this is your F square. I think now you got my point. Okay, clear? Okay. Uh, or you can also talk about, see, you can talk about rational numbers as well in this way. Okay, because in this case we are considering D to be a rational number, right? For example, if I consider, let's uh, say 8 upon 5, then I can write it as 2 upon 5 whole square times 10. So this D dash is called the square free part, and obvious enough that talking about q root D is equivalent to talking about q root D dash, right? Clear? So therefore, in the definition of a quadratic field, we can assume the rational number D to be square free. Okay. Okay. Now we can extend the concept of these quadratic integers, quadratic field, from rationals to integers as well. Okay, how do we do that? Now let D to be a square free integer. Okay, D to be a square free integer. Define Z root D to be the collection of all elements of the form a plus b root t such that a, b are integers. Okay. Now clearly enough that Z root D is contained in Q root D. So Z root D is contained in Q root D. First let us talk about a simple definition, that let R be a ring, then A contained in R is said to be a subring of R, if A is a ring with respect to same set of operations as R, okay. We always denote it as often A less than R. This is the symbol we often use. Okay. So clearly enough, if I imply this, so basically what a subring is, like we study subgroups, it's the subrings are resemblance of subgroups. So it's a substructure of a ring, right? So subring is a ring on its own right, but the thing is that it just considers the same elements as the ring it is contained inside, and the operations are also same. Okay, clearly enough. So therefore we can say that Z root D is a subring of Q root D. What more can we say about the quadratic integer ring? This is called the quadratic integer ring. This is called the quadratic integer ring. Okay. Now observe the fact that if I consider any square free integer, let x be a square free integer, then 4 will not divide x, because if 4 divides x, then x is no more square free, because 4 is basically 2 squared, right? Therefore if I consider a square free integer, therefore if D is a square free integer, then what should be the remainders of D when we divide it by 4? It can be 1, 2 or 3, it cannot be 0, right? Now we define an element W to be root D if D is congruent to 2 or 3 modulo 4, and to be 1 plus root D by 2 if D is congruent to 1 modulo 4. With respect to this element W, we define the group theta to be ZW, which is the collection of all elements of the form A plus BW, such that A and B are integers. Okay. Actually, this is called the ring of integers. This is simply called the ring of integers. This is a general notion. Okay, this is a general notion. Okay. Now, what are some special types of rings of integers which are actually important? Like one of the most important type of ring of integers is the ring of Gaussian integers. Let D to be -1, then so if D is -1, then D is congruent to 3 modulo 4, right? Then ZW is nothing but Z of I, right? Z of root of -1, Z of I. So it is the collection of elements of the form A plus BI such that A and B come from Z. This is called the collection of Gaussian integers, or the ring of Gaussian integers. Okay, clear? Okay. Now what we do is that we define a function on these ring of integers, which we call the field norm. Okay. This field norm will actually resemble, if you have done a course on non-linear spaces or vector spaces, inner product spaces as well, then if you have got a sense of what a norm is. A norm basically resembles a generalization of the concept of magnitude of a vector. So this field norm which we are going to define now, it sort of resembles the standard norm defined on complex numbers, or the standard absolute value defined on complex numbers. Okay, we define that concept on a general notion. Okay, define the field norm such that, so how is the field norm defined? It is defined from Q root D to Q by the norm of any element A plus B root D is A square minus DB square, is an element of Q. Surely enough, what we are actually doing is that we are multiplying the element A plus B root D with its conjugate. A plus B root D conjugate. Okay. Then we get the same set of observations, right? That is n of a plus b root d is non-zero if a plus b root d is non-zero, right? The thing which I said before moving on to this is that if uh, d is equals to -1, then n closely resembles the standard norm on C. Okay. So few important observations about n. Firstly, is that n is a multiplicative function. N is a multiplicative function. That is n of alpha beta is n of alpha times n of beta, where alpha beta are any elements from Q root T. You can check it out, it's very obvious. The next observations are what which we will be more focused on. Actually, we are trying to establish a sort of relation between these structures and some a very important number theoretic equation which we call the Pell's equation. Okay. Now, suppose I choose an element from theta. Okay. Say a plus b omega belongs to theta. Let a plus b omega come from theta. Then what is the norm of a plus b omega? Then the norm of a plus b omega is, by definition, it's a square minus, or I shouldn't write it in this way. I should write it as a plus b omega times a plus b omega bar. But actually, what will be getting through? See, a plus b omega bar is basically a minus b omega. Typically, it's a minus b omega. So it's a plus b omega times a minus b omega. But if I multiply it out, it will come out to be simply a square minus b square d if d is congruent to 2 or 3 modulo 4. But if d is 1 modulo 4, then you have omega to be 1 plus root d by 4, right? If you just distribute it out, you will get the answer to be a square plus ab plus 1 minus d upon 4 b square. Okay, clear? Now observe the fact. If I choose any alpha from theta, then if norm of alpha is equals to plus minus 1, then this implies a plus b root d times a minus b root d is equals to plus minus 1. But this implies that I can define the inverse of a plus b root d to be simply plus or minus a minus b root d. Right? I am talking about an arbitrary element of theta, right? So I simply replace this with omega. Okay, right? Observe that the condition for the field norm to be plus minus 1 was not mandatory if we would have considered elements of the form a plus b omega where a and b were rationals. Since we are talking about the coefficients coming from integer, that's why we require the field norm to be plus or minus 1. Otherwise, we would get a reciprocal, and having a reciprocal, it surely means that it is no more contained in the collection where the coefficients come from integers, right? I guess it's clear. Therefore, if the field norm of some element alpha coming from theta is plus or minus 1, then that element alpha is invertible, or that element alpha is a unit, right? So this implies alpha is a unit. Surely enough, we have considered a plus b omega to be alpha. What about the converse? Okay. Suppose alpha is a unit. That is, there exists some beta in theta such that alpha beta is equals to 1, but this implies that norm of alpha beta which is equals to norm of alpha times norm of beta, but norm of alpha beta must be norm of 1, right? So this must be norm of 1, but norm of 1 is by definition 1. So norm of alpha beta is 1. So now since norm of alpha, norm of beta, they both come from integers, sorry, they both come from, see, we are talking about norm of alpha beta, right? Now the norm of alpha, where alpha is of the form a plus b omega, where a and b are integers, so this surely resembles to an element from integer, right? So both are coming from integers, but this implies then that norm of alpha and norm of beta, they can only constitute the values plus minus 1 respectively, right? Either both is plus 1, both are plus 1, or both are minus 1. But that means, so when we started with alpha being a unit, so when alpha is a unit, we are finding that its field norm is plus or minus 1. Therefore alpha belonging to theta is a unit if and only if its field norm is plus or minus 1. But how does it help us? As I said, consider a Pell's equation. Consider a Pell's equation. So Pell's equation is basically an equation of the form x square minus dy square is equals to plus or minus 1, and we are to find integer solutions to it. But observe one important fact out here is that if I consider the element alpha to be x plus root dy, when x and y come from integers, then finding an integer solution to this is basically finding a solution to alpha such that n alpha is plus or minus 1, but that implies that finding an integer solution to this is equivalent to finding units in z root t, right? Got my point? Okay, or yeah, I shouldn't write z root d, I should write in z omega, specifically z omega, right? Okay, where omega has the exact definition as we were throughout discussing. Got it? There are some more similar sort of examples. For example, if I talk about elements from Gaussian integers, suppose I talk about Gaussian integers zi, then observe the fact that if I consider any element, say alpha from a plus zi, let alpha be of the form a plus bi coming from zi, then n of alpha is equals to plus or minus 1. This implies a square plus b square is equals to plus or minus 1, right? But for a square plus b square to be plus or minus 1, this implies that a is plus or minus 1, or this implies that for a square plus b square to be plus or minus 1, now it cannot be minus 1, right? It cannot be minus 1 at any cost, because a is coming from integers, b is coming from integers, so their square will be positive. Clear enough? What we can say is that a square plus b square is plus 1 precisely, but that means that a and b are 0 or plus minus 1 respectively, or let me write it like this, that is the number of elements which we can consider is that where a is 0, b is 1, a is 0, b is minus 1, a is 1, b is 0, and a is minus 1, b is 0. So therefore the only units in zi are plus minus 1 and plus minus I. Clear? One exercise, check that 1 plus root 2 is a unit in Z root 2. Okay. Check it out. Okay, or we can say it that simply we can write it as say Z omega, where D is equals to 2. Okay, try and check this out. Yeah, okay, so let's stop here. In the next lecture we will be discussing some more important examples. At least one example I'll discuss in the next lecture. Okay, rest of the examples we will be encountering at some point in our course, but one important example I will be discussing in the next lecture, which is the concept of group rings. This will surely be a content in the next lecture, but let's see if we can also include some more examples. So meet you guys in the next lecture.